Okay, so a uniform beam of weight 196 newtons and a length of 1 meter is attached to a hinge on the outside wall of a restaurant. The cord is attached to the center of the beam and it is attached to the wall, making an angle of 30 degrees with the beam. The cord keeps the beam perpendicular to the wall. If the breaking tension of the cord is 620 newtons, how large can the mass of the sign be without breaking the cord? So we know the first thing is that the beam is in an equilibrium. So both the net force and the net torque acting on it must be zero. So to find the maximum weight of the sign, I'll let the tension of the cord have its maximum value of 620 newtons, and we don't know the forces exerted by the hinge on the beam. So what I did was I choose the axis of rotation through the hinge, and then the forces exerted by the hinge of the beam, and it has a zero level arm and does not enter the torque equation. But before I did anything else, I drew my three pictures, and I drew my diagram, each force of showing the diagram on the beam, and I chose my rotation axis, and it's in the first drawing. And then from here, I drew each force vector starting from the point of the application, and I was able to find the torque by finding the level arm and find the perpendicular force, and then the distance from the axis from the point of the application. And again, my first drawing up here, right here, is just the sign hanging outside the restaurant, and the second one is the forces acting on the beam, and finally the third one is after I found the components of the tension in the cord. So now using this information, we can see that the gravitational force of the beam can be taken to act at the midpoint of the beam, since it is in uniform. So the force due to the cord has a perpendicular component, and that's why I use this equation here. For the perpendicular force is equal to 620 newtons times the sine of 30 degrees equal 310 newtons. So now the two gravitational forces tend to rotate the beam clockwise. So while the tension in the cord does rotate the beam counterclockwise. So the net torque must be equal to zero again. So now in finding that, I use this equation here of 1 meter times mg is equal to 0.5 meters times 310 newtons minus 196 newtons, and then we want to solve for m. So we get 0.50 meters times 310 newtons minus 196 newtons divided by 1 meter times 9.8 newtons per kilograms, and we get 5.8 kilograms.